friends. Welcome to the second session on process scheduling policy. Today we'll be discussing on the shortest job next or the shortest job first scheduling policy. I am Anuradha Sharma, Professor LJ College of Computer Applications, Vastrapur, Ahmedabad. Now, shortest job next or shortest job first scheduling policy is basically a non-preemptive scheduling policy. Now, what is a non-preemptive scheduling policy? This I have discussed in my previous session. But to just give you a brief idea, a non-preemptive scheduling algorithm is the one in which the CPU, once given to a particular process, cannot be taken away in between the execution. So, once the CPU is given to a particular process, that process keeps the CPU for the entire execution time, and after the execution is over, it releases the CPU on its own. Now, the detail about this, you can have a look at my previous video session. Now, shortest job next or shortest job first is the topic under discussion today. And to explain this, first of all, now shortest job next or shortest job first, it's, as I told you, it's a non-preemptive scheduling policy. In this policy, as the name itself suggests, shortest job first. That means the jobs are picked up from the ready queue based on their CPU time or the burst time. So the job which has the shortest CPU time or the shortest burst time is picked up for execution. Shortest job next, which we'll be discussing today, this is a non-preemptive scheduling policy. It also has a preemptive version, which we'll be doing in the next session, in my next video. And that is basically the shortest remaining time first algorithm. So coming back to shortest job next, we'll consider an example over here. Now we have 4 jobs, P1, P2, P3, P4, and their CPU time or the burst time, it is 12, 7, 4, 2, and their arrival times over here. Now, if I look at this example and if I understand about this policy, the shortest job first, now looking at this example, we can easily say that the shortest job over here is probably P4, which has a burst time of 2. So this job should be picked up for execution first. But in this case, if we see, the arrival time has been given over here. The arrival time indicates that at the arrival time 0, there is only one job over here, and that is P1. And an efficient system is that in which the CPU time is not wasted. So if at a time 0, there is only one job in the system, and whatever is irrespective of the burst time or the CPU time, the CPU is given that particular job. So in this example over here, at a time 0, there is only one job in the system, that is P1. Though it has a burst time of 12 milliseconds, but we don't know what is the burst time of the jobs to come in. So the CPU picks up this job for execution, and P1 at a time 0 is scheduled on the CPU. So this is the job which is currently getting executed in red. Now, P1 needs the job for 12 milliseconds. Now, since this algorithm is a non-preemptive scheduling, that means once the job gets the CPU, it will keep the CPU and will release it on its own only after the execution is over. So, P1 keeps the CPU till the 12th millisecond. Now, if we have a closer look over here, after the 12th millisecond, P1 is out of the system. Now, P1 finishes at 12, and by that time, all the remaining 3 jobs have entered the system. So, we have P2, P3 and P4. Now, since all the jobs are there and we are talking about the shortest job first scheduling policy, the CPU time or the burst time of all these 3 jobs are compared to find out which of these jobs has the minimum or the shortest CPU time or the burst time. Now, when these 3 are compared, we see that P4 is having the shortest time, that is 2 milliseconds only. So, P4 is picked up for execution, and now P4 at the 12th millisecond is put up on the CPU. P4 takes the CPU at 12 millisecond, needs the CPU for 2 milliseconds, so it continues the execution till 14. Now, as I told you, it's a non-preemptive scheduling. So once P4 needs the CPU for 2 milliseconds. Since it takes up the CPU at 12, it completes the execution at the 14th millisecond. And after the 14th millisecond, P4 is out of the system. So now we only have these two jobs remaining. So the job which is having a shorter CPU time or the burst time has to be picked up. So there is a comparison between P2 and P3. Now out of these two, P3 has a shorter CPU time. So P3 is now picked up for execution and is put up on the CPU. So at a time 14, when P4 leaves the CPU, P3 is put up on the CPU and it starts its execution at the 14th millisecond. Now P3 needs the CPU for 4 milliseconds. So it continues till 18 milliseconds because at 14 it took up the CPU. It needs it for 4 milliseconds. So it will continue till 18 milliseconds. And at the end of the 18th millisecond, it completes the execution and is out of the system. Now the only remaining job is P2. And at the 18th millisecond, P2 takes up the CPU. So here we have at the 18th millisecond, P2 is there on the CPU. It needs the CPU for 7 milliseconds. So it will continue till the 25th millisecond as it takes up on the 18th millisecond. It needs it for 7. So 18 plus 7 is 25. So it will continue to be there on the CPU till the 25th millisecond. And after the 25th millisecond, all the four jobs, they finish their execution and we have the timeline over here like this. P1 first, then P4, then P3 and then P2. If it would have been FCFS, it would have been P1, P2, P3, P4. But since in the shortest job first, the jobs are picked up based on their burst time. Over here we have P1 first, then P4, then P3 and then finally P2. So we have the timeline over here. Now, over here, if we see the timeline, we can have an idea. P1 at the 0th millisecond gets the CPU and it leaves the CPU at the 12th millisecond. Next, we have P4. At the 12th millisecond, P4 gets the CPU and P4 leaves the CPU over here. Now, why I am emphasizing over here on these things is that when a particular job gets a CPU and when the job leaves the CPU, these two things will be required when we calculate the waiting time and the turnaround time of the jobs. So P4 and then next is P3 at 14 milliseconds. When P4 leaves the CPU, P3 picks up the CPU. And at 18 milliseconds, P3 leaves the CPU. And then finally, P2 gets the CPU at 18 milliseconds when P3 leaves. And then it finishes off its execution and releases the CPU at the 25th millisecond. So now we'll be calculating the waiting time of the jobs and finally the average waiting time. Now what is the waiting time of a job? Now as the name itself is suggesting, it is waiting for something. Now what is it waiting for? It is waiting for the resource, and the resource over here is the CPU. So the waiting time over here is basically the waiting time required by a job to wait for the CPU. The amount of time a particular job waits to get the CPU, right? And when we calculate the waiting time, it is basically the time when a job gets the CPU minus the arrival time. Now here we have the arrival times given over here. So we'll be basically using these timings when we are doing the calculations. So waiting time of a job is time when the job gets the CPU minus the arrival time, and we'll calculate the waiting time of each job over here. So first of all with P1. Now P1 gets the CPU at the time 0. So and the arrival time of P1 over here is 0. I have given these two as the red color. So waiting time of P1 becomes 0 minus 0, that is 0 milliseconds. Next is waiting time of P2. That means how much did P2 wait to get the CPU. Now to see this, again we see the timeline. P2 over here, it gets the CPU at 18 milliseconds. So was it that it waited for 18 milliseconds to get the CPU? No. It came at the first millisecond. It arrived at the first millisecond on the system. So when it came on the first millisecond and it waited, it got the CPU at the 18th millisecond. So from 1 to 18, it waited for the CPU. It was waiting for the CPU. So 18 minus 1 is the waiting time of process P2, that is 17 milliseconds. Next we have P3. Now seeing the timeline, we can see that P3 gets the CPU at 14 milliseconds. So was it that it was waiting till 14 milliseconds? Again, no. It came on the system, it arrived on the system at the 3rd millisecond. So from 3rd millisecond till the 14th millisecond, it was waiting for the CPU. So 14 minus 3 is the waiting time of P3. Finally, P4. P4 got the CPU, as we can see from the timeline, it got the CPU at the 12th millisecond, right? And it came on the system at 4th millisecond. So it came on the 4th millisecond, it got the CPU at the 12th millisecond. So from 4 till 12, that is 12 minus 4, 8 milliseconds, P4 waited for the CPU. So these are the 4 waiting times of all the 4 processes, and we can calculate the average waiting time, which is the waiting time of all the jobs divided by the total number of jobs, which comes to 0 plus 17 plus 11 plus 8 divided by 4, which is 36 upon 4, which comes to 9 milliseconds. So 9 milliseconds is the average waiting time for all the processes if we consider shortest job first or shortest job next. Now, if we calculate the average waiting time using first come first serve, which you can do by referring to my earlier video. I have not shown the calculations over here, so you can refer to my earlier video to see how the calculations has to be done for first come first serve. If we do it using that policy, the average waiting time comes to 11.5. So as you can see from here, the waiting time is reduced to 9 milliseconds in case of SJN. So SJN, that is shortest job next or the shortest job first, is considered to be better. Talking about in terms of waiting time, it is considered to be better than FCFS. So this was about the average waiting time. Next is the average turnaround time. Again, the timeline, we already have the timeline. Now what is the turnaround time? I have explained it in my earlier videos. The turnaround time is the total time a particular job is there on the system. Total time it requires to complete its execution. Now over here, if we talk in terms of a formula, turnaround time of a job is time when the job leaves the CPU minus the arrival time. So as we have already seen in the timeline that in case of P1, P1 leaves the CPU at a time 12 milliseconds. It takes the CPU at 0, it completes at 12. So 12 milliseconds is the time when P1 leaves the CPU. And the arrival time for P1 is 0. So the turnaround time of P1 comes to 12 minus 0. So it was there on the system for 12 milliseconds. Next is P2, turnaround time of P2. Now P2 leaves the system, it leaves the CPU at the 25th millisecond. But it's not that for 25 milliseconds P2 was there on the system. P2 arrived at a time of 1 millisecond. So P2 was there on the system from 1 millisecond to 25 milliseconds. That is 25 minus 1, 24 milliseconds. Next we have P3. Now P3 leaves the CPU at the 18th millisecond, but it arrived at the 3rd millisecond. So the turnaround time of P3 is 18 minus 3, that is 15 milliseconds. Similarly, turnaround time of P4, seeing the timeline, P4 leaves the CPU at the 14th millisecond, but it arrives at 4 milliseconds. So the turnaround time of P4 is 14 minus 4, that is 10 milliseconds. So here we have the turnaround times for all the 4 processes. We can calculate the average turnaround time, which is the turnaround time of all the jobs divided by the total number of jobs, which comes to 12 plus 24 plus 15 plus 10 divided by 4, which comes to 61 divided by 4, and we get the turnaround time to be, the average turnaround time to be 15.25 milliseconds. Now, if if you just check up on my earlier videos, you will get the how to calculate the turnaround time, the average turnaround time using FCFS. So by doing that, we can find out that if we calculate the average turnaround time using the first come first serve policy, it comes to 17.75. And comparing it with SJF, where the average turnaround time is 15.25, we can again see that the performance using the shortest job next or the shortest job first policy is much better as compared to the first come first serve policy. So this was about the average turnaround time and the average waiting time using the shortest job first policy. Advantages of shortest job first policy: the first is that the jobs which have a shorter CPU time or the shortest burst time are favored. That means they are given the CPU first. And of course, as we have seen, that the average waiting time and the average turnaround time is much improved as compared to the first come first serve policy. The drawbacks of the shortest job first method is that suppose if the jobs keep on coming into the system, if we have many jobs coming into the system, and obviously because it is shortest job first, the jobs which are having the smallest CPU time will be picked up first. So the jobs which are having a large amount of CPU time will be put up at the back of the queue, and these jobs might go in for a situation of starvation. That is the drawback of probable drawback of a shortest job first policy. So this was all about the shortest job first, which is a non-preemptive scheduling policy. We'll be doing the preemptive version of the shortest job first, which is the shortest remaining time, in my upcoming video. So wait for that. Thank you very much.